Welcome friends, welcome you all in my channel Chemistry of Molecules. I am Tanmay. So today we will learn Peterson Olefination. Actually, it's a silicon analog of Wittig type reaction you can consider, because Wittig reaction we have seen this Wittig reaction actually phosphorus elide plus minus. For example, this minus Wittig. So when we called Wittig-Horner reaction, then actually it is this. So it's a carbanion type triphosphine oxide derivative type. But here you can consider this reaction is the silicon analog. So a silicon analog of that Wittig type reactions. Okay. So what happens? Actually the reaction is alkene preparation. But how this reaction, the process is occurred? First, so α-silyls are taken and reacted with magnesium in ether. So we know that magnesium reacts with this CCl to produce corresponding Grignard reagent. So this is Grignard reagent. So what happens is Grignard reagent, this is delta plus, this is minus, carbanion in nature and magnesium is in plus. So what is expected that this carbanion will attack with this carbonyl. Okay, so actually it happens, this goes and attacks this, and here it produces this magnesium reagent. It's simple. After hydrolysis, it produces this hydroxysilane. Okay, actually this is attached to another hydrogen also, and we know that carbonyl group is a planar, so attack possible from both sides, and ultimately it will result to diastereoisomer. What do I mean? Means position of these two may be different, means two stereo. So two diastereoisomer will produce in this reaction, and upon treatment of this one, and these diastereomers could easily be separated, and upon treatment with acid and utilize anti-elimination produces alkene, and in base it produces C-elimination. So the beauty of the method is, first of all, we can prepare these diastereomers and separate this diastereomer one to each other. First one. Second one is that scene elimination or anti-elimination based on our expectation could be achieved using this method. So this is the uniqueness of this method. So today what we will learn? So first we will learn about the basic concept that I have covered here. Second is mechanism. Third is the modification of this reaction, and fourth is diastereomer based final product. Okay, so let's start. As I told, basic concept I have explained. So let's discuss about the mechanism. What happens? This silyl alcohol, what happens? In presence of base, if base is given, for example hydride minus, like potassium hydride you can take. What it does? It abstracts this alcohol and produces hydrogen. So it releases hydrogen, and this silicon reacts O minus, and this is R. So we know the silicon have energetically accessible vacant d orbital, and it's like you can consider it's a phosphorus. And another thing you can consider, this is actually silyl carbanion. Okay, so its nucleophilicity is higher compared to simple ylides. So after that it produces this, and after this treatment it produces this alkoxide. Okay, and this alkoxide reacts. This alkoxide attacks here to form a 4-member ring. But in this case there is no proof that 4-member ring is formed. Okay, so this. Okay, you can consider here as R1. It will be better. This is R1. Then you can consider why diastereoisomer, because if I say CH2 then it could be an enantiomer. But here if I say R1, so here is one stereo center, means stereo center, one is another. So here there is two center, that's why it's a diastereomer. Okay, ultimately produces. So here R1. So this is a 4-member ring and undergo elimination. Utilizing, we can say here, to produce finally the silicon oxygen, and we know the silicon oxygen bond is stable due to multiple bond character, and that another thing is that lone pair, this electron density could be localized into the vacant orbital of silicon. So this is R1, this is R2. I am not saying it's this or that, its geometry is not sure. I'll explain later on. So this, and you can consider, since there is no proof that it happens through a 4-member transition state, you can think it in this way, that this oxygen attacks here and this leaves. So what will happen? It will generate a carbanion. Means this is a carbanion. This is R1, this is R, and O SI in it. Fine. Then it will attack, it will go. So whatever the thing, ultimately it will end up with this final product. Okay, this is base catalyzed. Now here one condition question appears. What question? For example, I am generating O minus, and the thing is that after hydrolysis I am producing OH, then O minus. Previously it was also O minus in case of magnesium. But why that time this thing didn't happen? Here is happening. Because the strength of this O-Me bond, because magnesium is also a 2p, oxygen is also a 2p. So whatever this bond is stronger, that's why this donation is not possible. Compared to this, if I take here the corresponding anion is potassium. Okay, and it was observed that this, in case of tertiary butoxide, if we take as a base, means MOTBU, it was observed that potassium is more reactive than sodium, there's more reactive than magnesium. Then you can understand the stability of countercation plays an important role for this, because that countercation drags some electron density towards itself. So attack by this oxygen is hampered. That's why this magnesium can't undergo this reaction. But is it possible when magnesium is used as a countercation, then it needs extreme conditions heating. So this is the factor. Okay. So till now we have understood this base catalyzed elimination pathway. So if instead of base, if acid is taken, what happens? So instead of base, if acid is taken, then it produces first, it is generate OH2 plus. This is R1. So this is R, this is R1, this is Si, this silicon region, and this is plus. So this acid goes anti, means instead of that, let's move this silicon this side. Okay, so goes anti, and then in this way the water molecule, actually acid means it's aqua acid, so protonated, so there is water, and you know silicon oxygen bond is stronger, and in order to form the silicon oxygen bond, this water goes and attack here, and this comes in this way, this goes. But lots of confusions are there in this case. Why? First of all, we are considering it as an acid. Okay, water will attack, but water we know is not a good nucleophile. First point, not good nucleophile. So there is a chance that it leaves early based on the acid strength and produces a carbocation. So carbocation means possibility of rearrangement. So carbocation means there is a possibility of rearrangement. So this confusion is there. How to avoid this confusion? It could be avoided by using HF as acid. Why? Because if we use HF, then the counter anion will be F minus, and we know that fluorine silicon bond is stronger, and fluoride is a very effective reagent to cleave silicon with carbon this bond, because fluorine has a good electronegativity, and we have used tetrabutane ammonium fluoride for silicon ether deprotection. Even oxygen silicon bond could be cleaved in presence of fluoride because this is so good. So please keep that in mind. So in this way reaction could happen easily. Another second point is, under aqueous condition HF is not a very strong acid. Under aqueous condition HF is not a very strong acid, it's a weak acid. So all the factor is followed. So in that case, if you want to follow acid pathway, it is better to use HF. Okay, so we have discussed about the mechanism. Now question, modification. So what type of modification could be done such that reaction becomes easier? Why I am saying easier? Because you can see 4-member ring is formed. So formation of 4-member ring is not easy, and when there is a chance of because this group has its own bulkness. This group. So if it want to form a ring, another thing, initially it may not be seen to each other. Always it could be depending on the bulkness of these even silicon. So that will be iron. So in order to achieve this to form this 4-member ring, they need to come cis orientation. So some energy is required. But this could be avoided using a modification like acetyl chloride or thionyl chloride. Both are similar type. You can see that labile CCl bond. What happens? This O minus attacks. Let me say this thionyl chloride bond. So it will come back, chlorine will leave. So what it will produce ultimately here? So it will produce a silicon R1 R, here O, here sulfur, here oxygen. Okay, my drawing is little bad. Let me draw it better. Sulfur, oxygen. So what is the advantage of this one? You can see right now, previously it was a 4-member TS. Right now it is a 6-member TS. So what happens? This bond comes here, this comes here, this comes here. So what ultimately produces? This ultimately produces, in this way the alkene is produced first. Along with that, this produces a SO, and this reagent is better, I believe better stable, because previously there is an anionic intermediate formed. Compared to that, this silicon is attached to oxygen, so that's good. Another thing, this charge is also balanced by attachment with this. What will happen if acetyl chloride is used? You can consider this acetyl chloride, just difference is that sulfur as well as methyl. So remove this sulfur and this is carbon and this is methyl. So similarly, and actually it is observed that this reaction, this conversion is achieved even around room temperature, that is around 25 degrees centigrade. So in this way, this base mediated olefination could be done easily. Okay, so this is the modification of this Peterson olefination. So right now we will discuss only the diastereomer based bond formation. So mainly this is actually, if you want to learn the basic part, this is done. So this is little I believe difficult, because now I am going to explain about the stereochemistry. So let's discuss about the stereochemistry part. So after this reaction, whatever the geometry of this center means this orientation, that will direct the product. What? So let's draw. Let's draw it in a Newman projection. It will be easier for you to understand. So if the attack could be done from both sides, and let's consider that this silicon reagent, silicon side is back and the carbonyl side is in front. Okay, so the silicon side means this one, this silicon trimethyl-silyl, it is attached to R1, and another part is, there is one hydrogen. So this is, and front part, so it will keep this part same. means one portion will be rotated because silicon reagent is same, it is carbanion, but the carbonyl group means that aldehyde we have used, that is changed, means RCOH. Okay, so that is going to change. So this is H. So one is one side, another is another. So that will be different. So this is O minus 1. If we consider R is here, so definitely that part will be another side. Means hydrogen is here, R is here. Okay. So this is the difference of 2. This is the difference of 2. Now, what we have told that the diastereomer separation is possible. Diastereomer separation is possible. So what does it mean? These two are diastereomers, so their separation is possible. And what is in reality, a particular diastereomer will provide a particular product. Okay. So right now means whatever this diastereomer will provide in acid condition and base condition, the exactly opposite thing will be achieved for this one. So I am not going to both individually, I am going to discuss only one. Okay, let's start. So in case of this, what will in case of this as this base promoted, for base promoted they need to come closer, means 60-degree rotation. So what will be the thing look like? The back part is same, means silicon R1H, and it will go 60-degree. So this O minus hydrogen R1. Okay. So these undergo elimination, means this part. So if this part undergo elimination, it will produce trans R1. Why trans? Because one side R1 and hydrogen, another side R1, one side R, this is R. This is one R hydrogen, another is R1 hydrogen. Okay, so ultimately this is another thing, R1 is front side, it is back side, so it is trans. But if we have taken that another diastereomer, it will give cis. So never we confirm that Peterson alkylation will provide cis or trans. It could not be concluded directly. It could be determined by the diastereomer we are using. Okay? Okay. So here, if we do the acid catalyzed one, what will be that? So for acid catalyzed, what will happen first? These will convert into OH2, and for elimination, it is better for anti-elimination. Why? Because I'll explain. Just first draw it. Anti means from here to it will come here 120 degree. Okay, so what will happen? So let's keep the back side same. Silicon trimethyl, this is H, this is R1, and so this is OH2 plus this, so hydrogen should go here and R should come here. Fine? Okay. This is because this is the sigma orbital. This is the sigma orbital and sigma star is here. Okay, here. So this electron will be given to the sigma star. How? Because as we said, fluoride will attack here. So this bond pair, this carbon silicon bond pair, means the sigma of these will means form a bond with the sigma star. So they will come in a proper alignment, and that alignment favors the bond formation and elimination easy. And actually this is a E2 pathway. Okay, so E2 pathway, what will ultimately produce? You can see this both R is same side, both hydrogen same side. So in this way these will produce cis alkene R1 R. So we have understood that under different conditions it will produce different alkene. So this reaction is stereoselective as well as stereospecific, because stereochemically different product results in stereochemically different, and a particular stereochemically product in a particular reaction will provide a particular one. So this is the overall discussion about this Peterson alkylation. So what we have learned today? First of all, reaction of this silyl carbanion to this aldehyde this is beta, this is alpha, this is beta. Beta-hydroxysilanol, actually Cl alcohol, that's why silanol. So beta-hydroxysilanol, and separation of beta-hydroxysilanol could be possible in using, because they are diastereomeric in nature, and at a particular diastereomer under a particular reaction condition, means acid or base will produce a particular alkene. Second point, acid always favor anti-elimination. This is true, means keep it in mind. Anti-acid means anti, base means syn. So, but why are we getting different from different? Because the stereoisomer. Okay, this diastereomer. So, this is the final discussion. So, next video I shall explain about JEE olefination. So, this is the end of the video. If you like my teaching, please give a like and share this video among your friends such that many people could be benefited from my info. And finally, please subscribe my channel Chemistry of Molecules, and please press the bell icon to get the notification of every single video I upload. So, stay blessed. See you in my next video.